157 kilometers of highway, 10 AI-powered machines, human supervisors watching from control rooms. China just achieved the world's first semi-autonomous paving operation.
In 2025, China built 157 kilometers of highway without a single construction worker lifting a shovel. 10 autonomous machines worked in formation while human supervisors observed from control rooms. Each machine made thousands of independent decisions every second, guided by sensors and satellites that offered accuracy down to the centimeter. The result was the first large-scale highway project in history, completed almost entirely by artificial intelligence. What unfolded on the Beijing-Hong Kong-Macau Expressway was not just another milestone in infrastructure, but a glimpse into how the physical world may be built in the future. The Golden Channel. The Beijing-Hong Kong-Macau Expressway is one of the most important transportation routes in Asia. Known as the Golden Channel, it links the manufacturing centers of the Pearl River Delta with the economic and political hubs of the north. Every day, it carries millions of vehicles, from heavy trucks transporting raw materials to passenger buses and private cars. The road is more than asphalt and concrete. It is a lifeline that sustains trade, connects families, and drives the growth of entire regions. Yet, it has also been the scene of chaos. In October of 2015, during the National Day holiday, more than 750 million people were on the move across China. At one toll station, 50 lanes of traffic were forced into just 20, and the result was one of the worst traffic jams ever recorded. Cars stood motionless for hours as far as the eye could see. From helicopters, the jam resembled a frozen river of steel stretching to the horizon. News outlets around the world called it Carmageddon.
This is the end of an enormous jam stretching over 4 kilometers, holding up people making their way back to Beijing from their holidays.
And the images became a symbol of the strain placed on modern infrastructure. For Chinese leaders, the event was not simply embarrassing, it revealed a deeper problem. The nation's infrastructure was modern yet still vulnerable. The scale of demand could outpace the ability of human labor to expand and maintain road networks. Traditional methods of construction required large numbers of workers, long schedules, and constant risk of delays. Even with massive investment, the speed of building was not enough to keep up with the pace of growth. The 2015 disaster became a turning point. If China wanted to sustain its development, it would need roads that could be built faster, smarter, and with more precision than human hands could provide. That idea planted the seeds for a new approach to infrastructure. Rather than relying on larger workforces, engineers began to explore whether machines could take on the tasks of paving, rolling, and compacting asphalt. China already led the world in using automation in ports, factories, and logistics. Extending artificial intelligence into construction was ambitious.
EV in cars, 5G, batteries, solar energy, now even in the AI, JAI, China became one of the players.
But it offered a possible solution to the bottleneck exposed by Carmageddon. Over the next decade, research and testing focused on creating machines that could operate without drivers, coordinate with one another in formation, and respond to real-time data with accuracy that surpassed human judgment. By 2025, the vision was ready to be tested. The Beijing-Hong Kong-Macau Expressway was chosen as the proving ground, and 157 kilometers of road would be built almost entirely by autonomous machines. The project was not only about completing a stretch of highway, but about demonstrating that infrastructure itself could enter a new era. When the 10 machines lined up at dawn on the opening day of construction, they were not symbols of replacement, but of transformation. They represented a shift from muscle and instinct to sensors and algorithms. And they carried with them the promise that future roads might be built with speed and precision once thought impossible. How did 10 machines working in formation replace an entire human workforce with such precision? The robotic crew. When construction began on the Beijing-Hong Kong-Macau Expressway, the site was unlike any road project the world had seen. There were no teams of workers in reflective vests guiding machinery, no foremen standing in the dust shouting instructions, and no drivers perched inside heavy vehicles. Instead, 10 massive machines lined up in formation. each one guided by an artificial intelligence system that operated with millimeter accuracy. Human supervisors sat in remote control centers, watching the process unfold on screens filled with streams of live data. At the center of this robotic team was the SAP 200C10 PA, a paver so advanced that it could spread 4 full lanes of asphalt in one pass. Its screed stretched 19.25 meters, wide enough to cover the entire width of the expressway. Moving forward, it laid down a continuous ribbon of hot asphalt, the surface glowing as heat shimmered into the morning air. To observers, it looked almost like a mechanical whale gliding along the roadbed, its bulk hiding the complexity of sensors, processors, and hydraulic systems working in perfect sync beneath the steel exterior. Behind the lead paver followed the rollers. They were organized in what engineers called a 1+3+3+3 formation. The single paver led the way, followed by 3 groups of rollers. The first group consisted of 6 double-drum steel rollers, each weighing 13 tons. Their job was to press the hot asphalt while it was still soft, smoothing it into an even layer. The next group included 3 enormous 30-ton rubber-wheeled rollers that provided the final compaction, pressing down until the surface achieved uniform density. Watching the formation in motion was like watching a choreography designed for machines. Each vehicle adjusted its speed, distance, and pressure automatically, responding to signals not from a human driver, but from the constant analysis of data. What set this project apart from earlier experiments in automation was the degree of autonomy involved. These machines were not simply following pre-programmed routes. They were making thousands of micro-decisions every second. The paver adjusted its screed angle if it detected a variation in the roadbed. The rollers increased or reduced pressure, depending on the compaction of the asphalt beneath their drums. Sensors measured temperature, density, and alignment in real time, feeding information into algorithms that learned as the work progressed. Humans monitored but rarely intervened, stepping in only if a malfunction occurred. The precision was made possible by China's Beidou satellite system, which provided centimeter-level positioning. Combined with radar, LiDAR, and infrared sensors, the machines could detect their environment with remarkable clarity. They knew exactly where the edge of the pavement lay, exactly how much pressure was needed to eliminate a soft patch, and exactly how fast they needed to move to maintain uniform quality across the full width of the highway. To engineers who had spent years training human crews to achieve consistency,
Chinese ventures, these are all sort of tools that China has used to help achieve these ambitions.
the sight of machines delivering perfect compaction without hesitation was astonishing. Safety was a major concern. Traditional construction sites are among the most dangerous workplaces in the world. Heavy equipment, extreme temperatures, and constant noise create an environment where accidents are common. Removing human operators from the immediate area reduced that risk, but it also required new layers of protection. Each machine carried electronic fencing systems that projected invisible barriers around its moving parts. If an obstacle entered the zone, the system triggered an automatic stop within milliseconds. Cameras and radar scanned for hazards, while communication networks linked the entire crew so that if one machine paused, the others adjusted instantly to maintain formation. One of the most impressive achievements was a technique known as zero-edge rolling. Human operators often struggled to compact asphalt at the very edges of a road without damaging curbstones or leaving gaps. The autonomous rollers solved this by using advanced tracking algorithms that allowed them to follow the pavement edge with millimeter precision. The result was a seamless surface that required almost no correction afterward. Engineers who inspected the finished lanes reported that the edges were among the cleanest they had ever seen. The technology inside each machine represented years of development by Sany, China's leading heavy machinery manufacturer. Engineers faced problems that had never existed before, such as teaching a roller to sense whether asphalt was properly compacted. They developed what the company called fusion self-sensing high-precision positioning. This meant combining data from multiple sources, infrared heat sensors, pressure monitors, GPS signals, and cameras, into a single understanding of the environment. The machine then made adjustments automatically, blending all the inputs into a decision-making process that functioned faster than any human crew could manage. The efficiency gains were clear. Traditional highway construction required dozens of workers across multiple shifts. Crews needed breaks, coordination, and constant supervision. Machines, on the other hand, worked with consistency hour after hour. They did not tire, they did not deviate from formation, and they did not require complicated handovers between shifts. This not only reduced labor requirements, but also increased the predictability of outcomes. A project that might have taken months could now be completed in a fraction of the time, with fewer defects and less need for rework. From the perspective of the supervisors watching from control rooms, the machines resembled an orchestra of steel instruments. Data screens displayed temperature curves, compaction readings, and positional maps. The supervisors could intervene at any moment, but more often than not, their role was to observe rather than control.
To pursue a self-sufficiency strategy in this advanced technology.
Each kilometer completed generated more data, and this data was immediately stored for analysis. Engineers could then refine algorithms, improving performance for the next section of road. In this way, the machines were not only building a highway, but also teaching themselves how to build better in the future. Observers noted the uncanny calm of the construction site, where human crews usually produced a constant background of voices, engines, and metallic clatter. The autonomous crew moved in near silence except for the low hum of engines and the hiss of asphalt being spread. Without the chaos of workers moving between machines, the site looked almost sterile, more like a laboratory experiment than a construction project. Yet, in that calm efficiency lay the promise of a new era, one where infrastructure could rise with less disruption and far greater consistency. The success of the robotic crew on the Golden Channel was not simply a technical achievement, it was a statement about the direction of construction itself. For centuries, building roads required immense human labor, from the stone paths of ancient Rome to the sprawling interstates of the United States. Now, China had shown that machines could take over nearly every aspect of the process. The 10 autonomous giants were not the final word, but the first chapter in a new story, a story where infrastructure might one day build itself without human hands on site. What happens when machines take over construction? Is it safer, cheaper, and what does it mean for workers? Safety, economics, and the human element. One of the biggest questions surrounding the project was safety. Road construction has always been one of the most dangerous professions in the world. Workers spend long hours exposed to heat, heavy machinery, noise, and traffic moving at high speeds just meters away. Removing people from the front line promised fewer injuries, yet it also required new systems to ensure that the machines themselves did not create risks. The engineers behind the autonomous crew designed multiple layers of defense. Every vehicle was equipped with radar and cameras that scanned continuously for obstacles, and electronic fences surrounded each machine with invisible barriers.
Each robot was equipped with electronic fences that created invisible barriers around moving.
If a foreign object crossed into the zone, the vehicle's emergency systems could bring operations to a halt within milliseconds. Unlike human operators, who might be distracted or fatigued, the machines responded instantly, applying brakes with precision and coordination across the formation. The other innovation was the communication system linking all 10 vehicles. Each machine operated independently but shared data in real time, creating a network where the behavior of one influenced the actions of the others. If the lead paver slowed down due to a detected surface irregularity, the rollers behind automatically adjusted their speed to maintain perfect spacing. If one sensor registered a potential hazard, the entire crew received the warning, and the formation shifted in response. In traditional construction projects, delays or miscommunication often caused mistakes, sometimes requiring expensive rework. Here, decisions traveled through a digital nervous system faster than a human could blink. The economic implications were just as significant. A traditional highway project of this length would require hundreds of workers across multiple shifts. Labor costs alone could run into tens of millions of dollars, not counting the expenses of housing, feeding, and transporting crews. Autonomous construction reduced that workforce to a small team of supervisors and engineers. While the machines themselves represented a substantial investment, their consistency and efficiency made them more cost-effective over the long term. They did not require overtime pay, medical leave, or rest days. They worked through the night if conditions allowed, and they delivered results that met or exceeded quality standards every time. To Chinese policymakers, this project was not only about building a road, but about demonstrating a new model of infrastructure economics. In a country that planned to add thousands of kilometers of expressways, bridges, and tunnels in the coming decades, the ability to cut labor requirements while improving precision offered enormous savings. It also allowed construction to proceed faster, reducing the downtime of routes that carried millions of vehicles each day. For the Golden Channel, which served as the backbone of national commerce, every day saved meant billions in preserved productivity. Yet, behind these statistics lay a more human concern. What would happen to workers when machines replaced their jobs? Highway construction had long employed vast numbers of people, many of whom relied on seasonal contracts for their livelihoods. As autonomous systems advanced, critics worried that these workers would be left behind. Supporters countered that, while some jobs would vanish, new roles would emerge. Designing, maintaining, and supervising autonomous machinery required skills that could not be automated. Instead of standing under the sun with a shovel or roller, future workers might sit in climate-controlled monitoring stations, programming algorithms, or servicing complex sensors. The debate over job displacement versus job transformation is not unique to construction. The same arguments have emerged in manufacturing, logistics, and agriculture as automation spread. What the Golden Channel demonstrated was that the shift had reached infrastructure, one of the last industries still dominated by manual labor. For centuries, road building had been synonymous with human sweat. Now it might become a field where expertise in data, engineering, and machine learning mattered more than physical strength. Observers also noted the psychological effect of seeing machines perform tasks once reserved for humans. To many, the sight was both fascinating and unsettling. There was something almost alien about the calm precision of the robotic formation, moving without hesitation or error. For older construction veterans, it felt like watching their trade evolve beyond recognition. Yet, for younger engineers, it was inspiring, a sign that they were entering an era where infrastructure could be built with the same technological sophistication as aircraft or microchips. The supervisors monitoring the project described their roles as closer to air traffic controllers than traditional foremen. Screens displayed constant streams of information, temperature gradients, pressure readings, positional maps, and live video feeds. Their responsibility was to watch for anomalies and intervene if necessary, but in practice, interventions were rare. The machines handled the vast majority of adjustments automatically. The supervisors often found themselves analyzing patterns rather than issuing commands, studying how the systems learned and improved over time. This shift in responsibility illustrated another economic impact. While the machines reduced the number of workers needed on site, they increased the demand for higher-skilled technicians. Universities and training centers in China were already adjusting their programs to prepare students for careers in autonomous systems maintenance and supervision. Just as the rise of automation in factories had created jobs for robotics engineers and software developers, the spread of autonomous construction promised to create a new class of specialists who could manage fleets of machines rather than individual vehicles. Safety, economics, and labor were all part of the same equation. The Golden Channel proved that roads could be built faster, cheaper, and safer by removing humans from direct exposure to hazards. But it also raised questions about how societies adapt when machines take over tasks once considered essential sources of employment. The project did not end the debate, but it gave the world a working example of what autonomous infrastructure looked like. And it forced policymakers, economists, and workers alike to imagine a future where roads and bridges might rise from the ground with minimal human presence. For China, the lesson was clear. The 2015 Carmageddon had shown the cost of outdated methods. The 2025 Golden Channel project showed the promise of new ones. The country had transformed a national embarrassment into a national triumph, not only solving a practical problem, but also positioning itself as the global leader in autonomous construction. While other nations debated regulations and safety standards, China was already laying down asphalt at machine-guided speed, turning vision into reality before the world's eyes. If machines can already build highways, what comes next for bridges, tunnels, and even entire cities? The future of autonomous construction. The success of the Golden Channel project was only the beginning. China's engineers made it clear that highways were the first step in a much larger strategy. Research was already underway to apply autonomous systems to bridge building, tunnel boring, and even large-scale assembly of residential blocks. The vision was to create a network of infrastructure that could rise without human labor, with machines working day and night, guided by algorithms and satellite precision. Other nations took notice. Japan announced plans to test robotic crews ahead of the 2030 World Expo, while the European Union began studying the Chinese model. Even the United States, despite ongoing trade disputes, quietly funded research into autonomous road construction. What set China apart was its ability to implement quickly. Where others debated, China built. Each new project added more data, more refinements, and more confidence that the future of infrastructure would be written not by shovels, but by machines. The Golden Channel proved that roads could build themselves. What comes next may redefine how human civilization creates the very foundations of its cities. The 157 kilometers completed by 10 autonomous machines represent far more than a construction milestone. They are a declaration that the age of human-only infrastructure is ending. And while roads, bridges, and tunnels will still serve people, they may no longer be built by people. China has shown what is possible when technology and ambition combine on a national scale. And the question now is not whether autonomous construction will spread, but how quickly. For centuries, the story of infrastructure was written in sweat and stone. Yet, from this point forward, it may be written in code and steel. And if you want to follow the next unbelievable projects that these machines are already moving toward, make sure to subscribe so you never miss the future being built before our eyes.